All right, so today we'll talk about alkenes. Unlike alkanes, in alkanes you can rotate around carbon-carbon single bonds. We saw that last time with this model of ethane where you can spin around the carbon-carbon bond. We talked about how staggered conformation is better than an eclipsed conformation. And then we talked about conformations of butane. Let's see if I can find butane in this list. And you learned to draw Newman projections with butane. B-U-T-A-N-E. Good. And you can see as drawn here, we're looking down the bond between carbons 1 and 2. And you can see that the methyl groups are what relative to each other? What's that relationship between the methyl anti, right? If I take the methyl group in the front and I twist it a little bit, it bounces back from an eclipse conformation and doesn't get to the next conformation. But if I give it a little bit more of a tug, it will go to a higher energy conformation called what? Gauche is the relationship between those two methyl groups. All right, so you can see, and the thing I hope I've convinced you is, yes, you can rotate around carbon-carbon sigma bonds. Not so easy for carbon-carbon double bonds. So let's see, it looks like this is the only, yeah, that'll work. So this is a molecule called 1-butene. The double bond is between carbon 1 and carbon 2. And then there are single bonds between carbons 2 and 3, and then 3 and 4. If you look down the bond between 2 and 3, you can totally rotate around that bond, no problem. 4 and 3. If you look down the bond between 2 and 3, you can also rotate around that bond without any problem. But, and the way to show that is really to grab this and torque it around. But if you look down the bond between the two carbons, the double bond between carbons 1 and 2, it's kind of hard to cite the molecule that way. Okay, there isn't free rotation around that bond. In other words, there's no way for me to take this hydrogen without, at room temperature, there's not enough energy for me to take this hydrogen and twist it around. So the one thing you need to understand about pi bonds is at room temperature, we don't rotate around pi bonds. Doing so would break the side-by-side overlap of p orbitals that make the pi bond. So that's going to mean for this alkene, it doesn't matter too much because, of course, on this carbon 1, the group here is a hydrogen, and the group there is a hydrogen. And even if we did rotate around the bond between the two carbons, we couldn't tell the difference. However, in a more complicated alkene, you'll see there are two distinct shapes that do not interchange. So let's draw 2-butene. This particular stereoisomer we can call trans 2-butene. This is an example of what we will call a di-substituted alkene. That kind of vocabulary just refers to how many non-hydrogen things are on the two carbons participating in the double bond. A little bit of other terminology that might come up in how we discuss molecules. Instead of saying the carbon that's participating in the alkene, I will say vinyl carbon. You'll wonder where you've heard that word before, and you've heard about it is in a plastic called polyvinyl chloride. Used to make records out of that, which are a thing that people used to play music on, though it's coming back, and you can now, instead of spending $1 on an MP3 or whatever, you can now spend $30 or $40 on a record, and you can listen to it in a record player and feel vintage and retro. Vinyl, in this case, and that polymer is made out of a molecule that's an alkene. And so that's one of the reasons why they call it polyvinyl chloride. But the two carbons participating in the alkene, the pi bond, are called vinyl carbons. And di-substituted means this vinyl carbon has a non-hydrogen thing attached to it, and this vinyl carbon also has a non-hydrogen thing attached to it. There can be a maximum, if you have both vinyl carbons in an alkene, there can be a maximum of 4 groups, 2 on each vinyl carbon. Di-substituted is when 2 of those 4 are not hydrogen. Tri-substituted would be 3, tetra-substituted would be 4, mono-substituted would be 1. So in this di-substituted alkene, the two non-hydrogen things, these methyl groups, are on opposite sides of the alkene. And if you looked down the bond between vinyl carbon A and vinyl carbon B, you would see that the two methyl groups would be anti to each other or opposite each other. Okay? Now, there's another molecule, another isomer, we would say, of trans-2-butene. It is also disubstituted, but we're going to call it cis-2-butene. And the reason we're calling it cis is because the non-hydrogen thing on vinyl carbon A is on the same side of the alkene as the non-hydrogen thing on vinyl carbon B. And in fact, if you looked down this bond between A and B, what you would see is vinyl carbon A in the front with a methyl group pointing straight up, a hydrogen pointing straight up and a methyl group pointing straight down. That's how this carbon would look would look like if you looked at it from a Newman projection. And then carbon B in the back we can't see, but we can see the hydrogen pointing up and the other methyl group pointing down. So that's the Newman projection for cis-2-butene. Just for fun, let's draw the same thing for trans-2-butene so you can compare and contrast. Again, looking down the bond between A and B. For vinyl carbon A in the front, you'd see the methyl group pointing down, the hydrogen pointing up. For carbon B in the back, you can't quite see it, but you'd see the methyl group pointing upward and the hydrogen pointing downward. Any questions about how I got those Newman projections? Go ahead.
So what determines if it's like, I know that trans and cis are different.
Yep.
Based on like their positioning, but is it based on, so like would something be cis if there's more tension, or between like those gauche, or those aren't gauche, those are, well yeah, are those?
They're eclipsed now, yeah.
They're eclipsed because of the double bond.
Yep.
Okay, so is that what determines something is cis?
So what do you mean by determines?
Because like why did you call that one trans in the first place?
The one on the left is called trans because the two methyl groups are anti to each other. That's the definition of trans.
Okay, so it's because I don't know. Like I see the difference. The difference is that instead of the methyl group is in places where the hydrogen was.
Right.
So
I think your question is how do you form different stereoisomers? No?
I think it's just based on if I were to look at like a skeletal molecule and determine if it's trans or cis.
Yeah, if we drew this without the hydrogens, the trans-2-butene would look like that. The cis-2-butene would look like this.
Yeah.
And so you'd look at where the non-hydrogen things are.
Okay.
If they're on opposite sides, that's trans. If they're on the same side, that's cis.
Okay.
Follow-up question, clarify? Are you okay? All right, go ahead.
Would that mean that the trans-2-butene is more stable in the molecule than cis-2-butene?
Well, the question is the trans-2-butene more stable than the cis-2-butene? Go ahead and make a prediction. Reason through it. What do you think?
I think that trans-2-butene is more stable just because the methyl groups are further away.
All right, and if the methyl groups, which are the large things, are further away, you're going to minimize steric repulsion, right? As opposed to here, the methyl groups are eclipsed, so that's maximum steric repulsion. In fact, we can build a space-filling model of trans-2-butene and cis-2-butene to demonstrate this. We do that in Spartan. Delete, yes. There's the trans. Let's look at space filling. The double bond, the molecules that are involved in the double bond are in the middle. The atoms involved in the double bond are in the middle. This is the methyl group on carbon 1. This is the methyl group on carbon 2. This is the methyl group on carbon 3. And you'll see that they are not bumping into each other. Even if we look down the bond between the two carbons, they the methyl groups are anti, as far apart as possible. In contrast, if we go delete one of those methyls and put it on the same side, we get cis-2-butene. And looking at the space filling model, you can see those methyl groups are in contact with each other. The hydrogens are even touching, meaning there's going to be electron-electron repulsion between these two groups. That's going to make, as you predicted, the cis isomer less stable than the trans isomer. Maximal steric repulsion, less stable. Minimized steric repulsion, more stable. So in general, the trans and the cis isomers have different stability. Trans is more stable than cis. Now, the important thing to realize is at room temperature, these are not interchanging. You can get to high temperatures where you have enough kinetic energy to break the pi bond temporarily and rotate around the double bond. But importantly, at room temperature or under the conditions where biology operates, you don't rotate around pi bonds. So if you have the trans, it's not going to turn into the cis, and if you have the cis, it's not going to turn into the trans, unless, of course, you break a pi bond. So these two molecules, interestingly, they are isomers of each other because they are not interchanging with each other. They're not in equilibrium at room temperature. And they're a special class of isomer. Like all isomers, they have the same molecular weight and the same formula. Unlike a lot of isomers, they have exactly the same connectivity. That is, they're both 2-butene. They both are a 4-carbon chain with a double bond between carbons 2 and 3. The difference is in their 3-dimensional shape. And the two 3-dimensional shapes are not, let's see, I can't spell that or write that, interchanging. So we're going to have a new term for isomers that have the same molecular weight, same molecular formula, same connectivity, but different 3-dimensional shape. We're going to call those stereoisomers. And I'm going to introduce, there's actually 2 different kinds of stereoisomers. I'm going to introduce one new term today and then another new term probably on Friday. Today's new term for stereoisomers is diastereomer. The cis and trans stereoisomers are diastereomers. That is, they are stereoisomers that are not mirror images of each other. Now, why the heck are we talking about mirror images of each other? Stay tuned till Friday. I'll explain. But right now, cis and trans alkene stereoisomers, the correct word for that is diastereomer. Okay? Questions about that? Okay. Like it says, if you've ever read the Christmas Carol, the first line is, Jacob Marley was dead. That is a doornail. And this one thing you must remember, or nothing that follows will seem wondrous. The thing you must remember so that things that follow will seem wondrous is cis and trans don't interchange at room temperature unless you can break the pi bond. All right, keep that in your mind. Now, it turns out the words cis and trans don't really work very well for larger molecules where there's more than 2 things attached to the vinyl carbons. For example, let me give you a simple alkene. How should I describe this alkene? Should I call it cis or trans? Well, I mean, how do you decide? Already, I think you're making some judgments about which group is more important to talk about, and that's fine as long as everybody knows the rules. For example, those of you that are saying, I want to call it trans, are probably saying, well, on vinyl carbon A, the methyl group is clearly most important, by example to what we did previously. And some of you are making the judgment that on vinyl carbon B, this ethyl group is most important. Okay? Just intuitively. Is that sort of what you were reasoning? So who put you in charge is what I want to know. Like, how did you know to do that? Yeah, go ahead.
You're always looking for the chain with the highest molecular weight to decide whether it's trans.
Okay. So one potential way to do this is to always look for the chain of the two things attached to vinyl carbon B, ask which one has the larger molecular weight, and then that may be the one you talk about when you're talking about trans or cis. Turns out that is a fairly sensible way to make the rules, but that's not actually entirely how IUPAC makes the rules. And in fact, if you go by that, you'll get the answer right some of the time, and you'll get the answer wrong some of the time, and it won't make sense. So it turns out there is a way to determine of the two groups attached to the vinyl carbon B, which is the most important that we're going to talk about. And the rules are summarized in this handout here. If you didn't get one, I've got some more there. It's also public. It's also posted on the content page of Learning Suite, so you can look it up if you lose it. It's a few pages long, and it sort of describes these rules. We don't need all of that time to describe the rules, but it does take it through. It does take you through it stepwise, and if you need some practice, this is useful. It turns out that for stereoisomers, or for alkenes that have 3 or more non-hydrogen things attached, we drop the cis-trans system and we use the E and Z configuration system. And this is a simple set of rules for deciding for vinyl carbon A and vinyl carbon B, which are the two groups we're talking about. And the rules are set, everybody knows them. You can make a computer program that figures them out for you, so that when you say this alkene has a Z configuration, there's absolutely no confusion and everybody knows what you're talking about. And if you say the alkene has an E configuration, same thing. So let's go through the rules for assigning stereochemical configuration, whether something's E or Z, and then we'll practice, okay? First thing to do conceptually in your mind is look at either vinyl carbon independently of the other vinyl carbon. So in my mind, I draw a squiggly line down the alkene. I focus first on vinyl carbon A, and then I go to vinyl carbon B. The first question that we're going to ask is, are the two things attached to the vinyl carbon that you're looking at same? Are they the same atom or different? Hold on. Let me back up a little bit. Are the two things attached to the vinyl carbon overall, are they the same or different? And by same, I mean same all the way out. If they're same all the way out, then you get to stop and no stereochemical configuration is necessary. No stereochemical configuration EZ assignment is necessary. So an example of that would be this alkene. Vinyl carbon A, vinyl carbon B. Just looking at vinyl carbon A, they're both methyl groups, right? They're the same thing. So it turns out you could draw, there are no cis or trans stereoisomers. Those two are actually the same thing. Can you convince yourself that they're the same thing? To see how to do that, let me give you a hint if you can't. Slide your molecular spatula underneath this molecule like a pancake and then flip it over like that. And it's the same thing. Questions about how to see that? Yeah?
Well, just going back a little bit, you said like all the way out. What exactly do you mean by that? Like to the end of the molecule?
Well, right. So for example, the other, all the way out applies here. For example, you could look at vinyl carbon B and say methyl group, oh, they're both carbon. so it's the same thing. No, they'd have to be the same all the way to the end of either chain. Yeah. Okay, so the first thing, yeah, you gotta evaluate are the two things attached the same thing or different? If they're the same thing all the way out, then stop. There's no need to assign stereochemical configuration. If no, the second question you ask is, are the atoms directly attached to the vinyl carbon the same or different? If different, heaviest atom has priority level number 1. So, looking at our example molecule here, for vinyl carbon A is attached to a carbon and a hydrogen. They're different. Therefore, the heaviest atom has priority level 1. It gets to get on the airplane first and take all the overhead compartments and drink champagne in first class and then watch the rest of the carbons come in walking. Oh, sorry. Have you guys been on planes lately? Isn't that painful? Have to walk past those jerks in first class on your way to coach, you know. All right. Well, anyway, this is not a commentary about airline travel. Okay. So for carbon A, it's easy. For vinyl carbon B, you look at this group here and this group there, and they are both carbon. So if they are the same atom, then you ask, what is each atom bonded to the vinyl carbon? What is each atom bonded to? And you're going to write down the atoms that atom is bonded to in order of weight or atomic mass, atom by atom, and you're going to count each bond. So double bonds would count twice. Looking up here, the pink carbon attached to vinyl carbon B is bonded to one other carbon and then 3 hydrogens, whereas the blue carbon attached to vinyl carbon B, do you see that it's bonded to 2 carbons and 2 hydrogens? And do you see how I wrote that in descending order of size? Okay? Once you've done that, writing down, then you compare the lists atom by atom, and heaviest atom wins. So, comparing the lists, carbon versus carbon, that is a tie. Go to the next one. Carbon versus hydrogen. Carbon wins. Therefore, winner takes all. This is the priority group 1. Okay? Yes?
So the weight is basically just based on the
Atomic number or atomic, yes, the mass number, yeah. Carbon is 12. Yep, hydrogen's 1. Notice that I did not, and this is the distinction from what you said earlier, that we're comparing atom by atom. We're not saying, let's add up all the atoms in the ethyl group and see what it weighs versus the methyl group. Instead, we're doing it more slowly, atom by atom. Okay, finally, once you've got a difference, once you've got a winner on both sides, if the priority group on vinyl carbon A and priority 1 group on vinyl B are on the same side, we're going to give it the configuration Z, which is sort of the equivalent of cis. If they are on opposite sides, we're going to give it the configuration of E. These are actually abbreviations, first letters of German words. The German word that means together is zusammen. And if you have a hard time remembering that, just say the groups are on the same side, but use a Z. They're on the same side of the alkene. That was not even worth a chuckle. That was worth a slight exhale. Huh. Okay, same side. E is for the German word entgegen, which I think means opposite or apart. So I don't know how you're going to remember that. Opposite ends with an E, but so does same. So does that really help? I don't know. Figure it out. So what would we say for this alkene? Is it E or Z? E. So a complete name for this molecule now is going to give us the stereochemical configuration of the molecule. Now this is a 1, 2, 3, 4, 5 carbon chain. That's a pentene. The double bond is between carbons 2 and 3. And let's see, we also need to say the location of the methyl group, which would be 3-methyl. And then we're going to put in parentheses at the front of the name E. E3-methyl-2-pentene. And that tells you everything you need to know about the structure of the molecule. If there were multiple double bonds in the molecule, we would have to specify the double bond in front. We would have to write the number 2 in front of this letter E to indicate that the pi bond between 2 and 3 has the E configuration, and we do that for the other alkene in the molecule. Yeah?
Is it only one, or yeah, I guess the carbon, because it only has one more chain than the other side?
Right, the reason this one wins is because it's bonded to 2 carbons and 2 hydrogens instead of just 1 carbon. So it turns out that you would get the right answer if you just added up the whole weight of the chain here, but there are cases where you won't. So do it this way, atom by atom. Okay, go ahead.
But you only do that if it's the same.
But you only do that if it's the same atom.
If it's different.
If it's different, it's easy. Yep, one decision. All right, the best way to do this is just to practice. So let's look at your quiz where I've given you a ton of these. Let's maybe do a couple of them together and then I'll turn you loose. This first molecule is called geraniol. It's an essential oil from roses. Has kind of a rosy smell. We've got, I suppose we could start numbering 1, 2, 3, 4, 5, 6, 7, 8. So we've got pi bonds between carbons 2 and 3 and pi bonds between carbons 6 and 7. So let's start with the bond between 2 and 3. When you're first starting this, it will be helpful for you to draw in the hydrogens at least attached to the vinyl carbons that are implied but not shown. So there's the hydrogen on carbon 2. Now remember how we do this. Divide the pi bond in half. We're going to consider vinyl carbon 2 and vinyl carbon 3 separately. The first question we ask for vinyl carbon 2 is, what 2 atoms is it attached to? Carbon and hydrogen. Are they the same? No. Heaviest one wins. So this carbon is priority group 1. Right away. That's easy. Easy, get it? We're assigning E and Z and it's easy. That's even less worthy of an exhale chuckle. My sons have started recently to rate my dad jokes, so I'll say something and they'll, instead of laughing or groaning, they'll say, 3 out of 10, Dad. And I'd say, you think you're insulting me, but that's what I was aiming for. Mission accomplished. All right, carbon 3, vinyl carbon 3. What 2 atoms are attached to it? Both carbons, so that's a tie. They're the same, so we now have to consider what each carbon is bonded to. So first, look at this one. That's a methyl group. This carbon is bonded to carbon 3, so I'm going to write carbon here, and then the methyl group, and if you want to, you can draw in the other bonds that are implied but not shown, 3 other hydrogens. Okay, now let's do carbon 4. And you, as I said, you may want to draw in the hydrogens that are implied but not shown. Carbon 4 is bonded 2 times to carbon, once to carbon 3 and once to carbon 5, and then 2 times to hydrogen. So then we're going to go down the list. Carbon versus carbon, that's a tie. Go to the next one, carbon versus hydrogen. We have a winner. Carbon 4 is our priority group 1. Therefore, what is the correct configuration between 2 and 3? E, good. All right, now, good. Now do that for the pi bond between 6 and 7. Go ahead.
So E just means they both have a priority 1 bonded to the final carbon?
Sorry, say that again.
E just means they both have a priority.
No, E means the 2 priority 1 groups are on opposite sides of the alkene.
Okay.
Or if we look down the Newman projection, they are anti to each other. Yeah, E means the priority 1 groups are opposite or anti to each other.
So if the methyl happened to be like the priority 1, that would be Z?
Right, if by some chance the methyl had something on it that would make it win, that would be Z. Yep. Okay, any comments yet on that bond between 6 and 7? Go ahead.
On the priority 2 carbon, it's the same 2 groups.
On carbon 7, vinyl carbon 7, you got 2 methyl groups. So, what does that tell you to do? Stop. Do not pass go. Do not collect $200. That is a reference to a game called Monopoly, in case many of you did not grow up in the 80s. I mean, they still have Monopoly, right? Yeah.
We play Monopoly Deal.
Monopoly Deal. Okay, what does that mean?
It's like a card game.
Card game. Okay, I need to know more about that, I guess. My youngest son used to like to play Monopoly Empire with me, which is something with towers and tokens and they can steal stuff. Anyway, go ahead.
I'm trying to find it in my notes here because I know you just said it, but can you explain just very simply why you stopped there?
Right, when you find 2 groups that are the same on one vinyl carbon, you actually cannot assign priority to either or the other because they're exactly the same.
Yeah, can you explain why they're the same?
This is a CH3 group and that is a CH3 group.
Okay.
Yep. So to determine whether groups are the same or not, you may need to write in the hydrogens that are implied but not shown. But this carbon is bonded to 3 hydrogens. This one's also bonded to 3 hydrogens. Those 2 methyl groups are identical to each other. Meaning you could try to assign priority, but you would rapidly determine that it's a tie all the way out. You can't discern between those 2 groups. And if that's true, then you don't have to assign E or Z. Yeah?
For the first group that we did, the Sp2025 bond, is that just basically telling us to ignore the stuff to the left?
While we're considering vinyl carbon 2, yes, we're ignoring the stuff to the left. And while we're considering vinyl carbon 3, we're ignoring the stuff to the right.
So with that carbon, would we associate that with having 3 hydrogens then?
Which carbon?
The carbon 2.
We never actually have to ask how many carbons 2 is attached to, because the thing we're doing is we're comparing the 2 atoms that are attached to carbon 2.
But still ignoring the other carbon that carbon's
As we go through this process, 2 is the vinyl carbon, the blue one and the hydrogen are the 2 things attached to it. We're only asking these questions, are they the same or are they different about these 2 things that are attached to carbon 2? So we never come back to carbon 2 and I feel like I'm not understanding the question. You want to try again? I want to make sure I get this.
I'm just a little confused because carbon 2 is technically attached to carbon 3.
Uh-huh.
So wouldn't it be a carbon-carbon as well?
It is a carbon-carbon double bond, but I'm confused as to why that matters. So I think you're worried about how to count what is bonded to this carbon. So let's talk through that. I'm going to tell you this process actually never has you answer that question, never actually has you ask that question, but you want to know it, so I'll tell you. This carbon is bonded to a hydrogen, another carbon. Oh, I see, okay. Yes, I'm going to ask what's bonded to this vinyl carbon 2, ignoring vinyl carbon 3. So I'm pretending for the moment that vinyl carbon 3 doesn't matter. When I ask what is 2 bonded to, I'm only considering the 2 things on this side of the double bond. You're right, it's got 2 additional bonds to carbon, which is fine, but that doesn't actually tell me anything to assign configuration. So when I'm considering vinyl carbon 2, that's why I drew the squiggly line. You're going to ignore carbon 3 entirely, just focus on the other 2 things that are bonded to carbon 2. Does that make sense? Okay. All right, so you can see that for the pi bond between 6 and 7, there is no configuration necessary. So if we wanted to name this molecule IUPAC-wise, you've got 1, 2, 3, 4, 5, 6, 7, 8 carbons in the longest chain that contains the highest priority functional group, which is an alcohol. So we know the suffix would be -all. There are 2 pi bonds, one between 2 and 3 and one between 6 and 7. So this molecule is a diene-ol. We need to put non in front of nona in front of diene to indicate that there are 9 carbons. So nonadiene-ol. We need, sorry, what? Oh, octa. Yeah, thank you. I wasn't trying to gaslight you. There are only 8 carbons. Octadiene-ol. We need numbers to say where the pi bonds are. So that's 2 and 6. Octadiene-ol. Then in terms of other substituents, what do we got? Just the methyl on, oh, there's 2 methyls. So it's 3,7-dimethyl. 3,7-dimethyl 2,6-octadiene-ol. And then in front of that, we need to put an E to indicate the stereochemical configuration of the 1 alkene. Now, you technically don't need a number in front of that because you can only assign E or Z to the first alkene. And if you tried to draw this, that would be obvious. You draw the methyl group on carbon 7 and you would see, oh, that alkene doesn't have stereoisomers, so it doesn't matter. But if you want to, it's not incorrect to put 2 in front of the E to indicate that we were talking about the bond between 2 and 3. Yeah?
Can you show us what it would look like if 6 was, if we just said that it was a stereoisomer? What would that be?
So you want to see, oh, what if, okay.
And what's the name of that?
Yikes. You want me to change the molecule and give you a different name. Okay. So I added another methyl group. Now I get my nonadiene-ol. You don't have to write this down. If I did that, these 2 would be the priority 1 groups. This would be also E. I'm just doing that in my head because we're going through it quickly. You would do 2E, 6E, and so on. Now that's not the problem I gave you, but that's how you'd handle it with multiple alkenes. All right, I'm going to turn you loose on linolenic acid, which is an unsaturated fatty acid. Those ones should all be pretty straightforward, but give it a try. See what you come up with. Take 2 or 3 minutes. Okay, got anything on that linolenic acid? How about the double bond between 9 and 10? You're saying cis would work, right? Because there's that alkene only has vinyl carbon 9 and vinyl carbon 10 only are bonded each is only bonded to one non-hydrogen thing. So it would be totally fine to call that cis. It would also be fine to call it Z, okay? Z or cis is fine for that one. But if I ask for EZ, stereochemical configuration, then tell me Z. Any questions about how you made that decision? On either side, it's carb. Go ahead.
So in the other example, when we got to the end where they was bonded to the same thing
Yeah.
on both sides, isn't that the same situation with the Z?
So isn't it the same situation that, I'm glad you asked. This is great. First, okay, couple of things. You don't actually have to, you're worried that, backing up. The time you don't need to worry about E and Z is where the two things attached to the individual vinyl carbon are the same. You can assign E or Z when the two things attached to either of the two. For example, with transbutene, it didn't matter that the two blue things were both methyl groups. The only thing that would matter is if this one and this one were both methyl groups.
Okay.
Yeah.
Wait, can you explain that one more time?
Yeah, the question was, if I'm looking at a pi bond like this and I see that the thing attached to vinyl carbon A that I've assigned priority 1 and the thing attached to carbon B that I've assigned priority 1, if they're both identical to each other, doesn't matter. You can still assign E or Z, because assigning E or Z is all about only looking at each vinyl carbon individually. Carbon versus hydrogen, carbon wins. And that's the exact same situation we're on in the quiz for 9 and 10. Look at vinyl carbon 9, carbon versus hydrogen, carbon wins. Look at carbon 10, carbon versus hydrogen, carbon wins. Yep, so you can call that Z. Other questions? Yeah.
Maybe I'm just so confused. So why can that also be cis?
Cis is okay when the alkene is disubstituted. And it's obvious what you're talking about.
What does that mean, disubstituted?
Disubstituted means, okay, this is an unsubstituted alkene because none of the vinyl carbons is bonded to a carbon. This is a monosubstituted alkene. This is a trans disubstituted alkene. This is a cis disubstituted alkene because you have two non-hydrogen things. This is a trisubstituted alkene. This is a tetrasubstituted alkene. If your alkene is disubstituted, there's 3 ways to do a disubstituted alkene. These two, and then the other that I didn't draw, which is this one. For this one, you can't assign stereochemical configuration, so who cares? For this one, it's obvious which groups you're talking about, so if you want to say cis, that's fine. Similar here, for this one, it's obvious the two groups you're talking about, so if you want to say trans or E, both of those are fine. If you get to be trisubstituted, then you got to go through E versus Z to assign stereochemistry. You can no longer use cis or trans because cis or trans are relative terms. This group is cis to that group, this group is trans to that group, and you use the priority rules of E and Z to determine which groups you're talking about. So for disubstituted alkenes like this one, where carbon 9 is bonded to one carbon and carbon 10 is bonded to one carbon, cis would be fine. Z would be fine too. And same thing for the others. Hopefully you've seen that the others are Z. Yeah?
Yeah, I know this is where it gets to the point where there's no reason to name it, but can you name it for us, please?
Okay. Would I expect you to name it? No, because I don't actually know the root for 18. But if you could, it would be a 9Z, 12Z, 15Z, 9, 12, 15 trienoic acid.
It's octadeca.
Octadeca, 9Z, 12Z, 15Z, octadeca 9, 12, 15 trienoic acid. And you can see why we stopped doing that, right? Yeah. But people will use this non-systematic name, linolenic acid, but they'll still say the double bonds are 9Z, 12Z, 15Z. So you do need to be sort of conversant in that to talk about things. This is a fatty acid that's found in triglycerides from like olive oil and vegetable oil. All right, lastly, you can do a couple of notes here. I want you to do this one as an exercise after class. There's no configuration needed here. And the reason you could assign one, but it's unnecessary because the alternative stereoisomer is not possible in a 6-membered ring. What am I trying to say about that? Well, notice that there are 6 carbons in this ring, and that carbon 1 and carbon 4 are on the same side of the ring. Now, try to draw me a 6-membered ring where carbon 4 and carbon 1 are on opposite sides of the ring, and 2, 3, you just can't, there's no way to stretch from 3 to 4. You can't connect a bond with you can't connect the ring closed with a double bond in a ring of that size. That's a minor point. I just wanted to tell you why you don't have to assign the double bond in that ring. Go ahead.
What about a 5-carbon ring?
5-membered rings, this is not for this class, but because you're curious, the minimum size ring that can accommodate a trans double bond is an 8-membered ring. Anyway, real quickly, assign the configuration between 9 and 10. On 10, what is my high priority group? Carbon 11, because it's carbon versus hydrogen. You don't need any other questions than that. How about on carbon 9? They're both carbons, so then you need to go what they're bonded to. The methyl group is bonded to 1 carbon and 3 other hydrogens. Carbon 8, now this is interesting. How do you do a carbon that's involved in a pi bond? You count sigma and pi bonds twice. So carbon 8 looks like it's bonded to 3 carbons. Now you could say, hold on there, buddy, it's only bonded to 2. And I say, I agree with you, but being doubly bonded is higher priority than being singly bonded, and that's how we account for it. So you count each bond to another atom independently, sigma and pi separately. That's why the list for any carbon should always be 4 atoms long, even if it's an alkene carbon. Does that make sense? So it wouldn't matter too much here. Carbon versus carbon is a tie. Carbon beats hydrogen in the second round of the tie-breaking procedure. So we would call that double bond what? E, opposite sides. Good. Yeah?
Okay, I had a question about how you named, like how you started. It's an unrelated, it's a different question, but so on the molecule, you started with the 1 inside of the ring,
Right.
How come you didn't start the carbon chain on that method?
Right, so you've noticed that I started the 1 in the ring instead of all the way out with the aldehyde, which is the right IUPAC way to name this thing, is to name it starting with the aldehyde, carbon 1. The reason I did this is because this is infuriating, but chemists and biochemists started talking about molecules long before the IUPAC folks got together and said, whoa, 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 we need to systematize this. And they named this molecule retinal because it's found in your retina. And there actually is a good reason for numbering with this carbon here. It has to do with the biosynthesis of it. That's a story I can tell maybe another time. But that's the non-standard numbering scheme. So no, you're not meant to infer from that we're not attempting to name this according to IUPAC rules. We do want to get good at assigning configuration. In particular, I wanted you to pay attention to the reason why this is called 11-cis retinal. So why do you think it's called 11-cis retinal? Look at the bond between 11 and 12. It's cis, or Z, right? All the other double bonds, if you were to assign them, I still think you should go through this yourself, but I will just tell you that all the other double bonds are E, and it's only that one that is Z. And what did I tell you about cis versus trans and their stability? Which is more stable? Trans, right? The reason for that is that the groups on carbons 10 and 13 are actually bumping into each other. The little half circles pushed together like that represent the space-filling atoms like I showed you in Spartan bumping into each other. So the cis configuration in 11-cis retinal is not the most stable configuration. In fact, the stereoisomer, where that double bond between 10 and 11 and 12 would be E, or trans, is more stable. So what does this have to do with vision? This molecule, 11-cis retinal, gets taken into your rod and cone cells, and it gets conjugated to or bonded with a protein called rhodopsin. And this is the chromophore in your eyes. It's the thing that absorbs light. So how it gets attached, you're going to learn that soon after the first exam. You don't know it now. But for right now, what you're going to see as we scroll down to the next question is that this aldehyde is no longer there. The oxygen is no longer there. Instead, the oxygen is going to be replaced by a nitrogen, and the nitrogen is going to be bonded to other things. So here are two examples of retinal conjugated to the protein opsin to make a molecule called rhodopsin. And if we start here, 1, 2, 3, 4, 5, 6, 7, 8. Well, that was, whoa, tripping. Okay, figured itself out. 7, 8, 9, 10, 11, 12, 13, 14, 15. You can see that this used to be the aldehyde carbon, and now instead of the aldehyde oxygen, there's a nitrogen, and the nitrogen's attached to something else. Don't worry about that. That functional group is called an imine, and you will learn how to make them later. That's coming up in a future chapter, but for now, all this molecule is attached to the protein, okay? And it's got this cis or Z configuration about the bond between 11 and 12. And that should be less stable than the trans configuration. So 15, 14, 13, 12, 11, 10, 9, and so on. You can see that to the to the left, the bond between 11 and 12 over here is Z. I get that wrong. Nobody was going to call me on that. The bond on the molecule to the left between 11 and 12 is E, or trans. Sorry about that. Let me say that again. So this molecule is 11-cis retinal conjugated to the protein opsin. This is 11-trans-retinal. The trans isomer is more stable. Notice that all the other double bonds have stayed the same. If we make these assignments, you would see E, 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 E. Over here, it would be E, E, Z, E. So the only thing that's changed between these two is the configuration of that alkene between 11 and 12. I'm not sure why it's glitching like that. I apologize. All right. Now, those two don't interchange with each other, right? They're stuck. But you can see what it would do if you could isomerize from cis to trans. If you could isomerize from cis to trans, that would cause this large group here to swing down this direction. And that would be a fairly large change that the protein could detect. Go ahead. You can't isomerize because of the pi bond unless you break the pi bond.
So why even do cis versions of these molecules exist?
Well, I'll tell you, because that's the beauty here, is the story is light is going to make this isomerization happen. In your eyes, the cis bond between 11 and 12, the Z bond, isomerizes to trans, or E, through something called photoisomerization. Okay? So how does that work? Just imagine, for a smaller molecule, if we just had one alkene, and I wanted to be able to rotate about the bond, I would need to break the pi bond, right? How could I break the pi bond? Go ahead.
Is that photon bump the electrons into the pi star?
Right. So in this molecule, you have a bunch of sigma bonds, then you have the pi electrons. Then up here you have the LUMO, which is the pi star. What happens when a photon of light is absorbed by the molecule and excites an electron from the HOMO to the LUMO? What does that do to the pi bond? Breaks it. Then you can rotate, right? Now this molecule 11-cis-retinal is special. There's a property we haven't talked about, and we probably won't talk about it too much, but the pi bond between 11 and 12 is not an isolated pi bond. As you can see, it is adjacent to several other pi bonds. And when that happens, the p orbitals associated with each pi bond line up together and make an extended system of molecular orbitals. And when that happens, the gap between HOMO and LUMO gets pretty small enough that visible light can excite an electron from HOMO to LUMO. For normal alkenes, it's usually ultraviolet light that can do this kind of thing, but for 11-cis-retinal, because of all of the double bonds that are adjacent to each other, the photon that excites from HOMO to LUMO is in the visible region, okay? So this 11-cis-retinal is spring-loaded. It's like a mouse trap, and as soon as it absorbs a photon of light, boom, pi bond breaks, it isomerizes, and now the computer's asleep? Seriously? There's some weird things going on today. Sorry about that. All right, so that's a major change inside the protein. That mousetrap action causes the protein to change its shape. Go ahead.
This is kind of going back a little bit. So you said it's 11-cis because of the one Z bond, or like the one Z.
Right.
So kind of one bad apple ruins the bunch, right?
Why do they call the whole thing 11-cis? They're assuming that you know that everything should be see, it's just the history that's built in. They only call it 11-cis-retinal. They're ignoring all the other double bonds when they call it this. They're just focusing in on the one thing that's important about the molecule. If you were going to be given an IUPAC name that would tell you how to draw the whole thing, it would need to have way more information than that.
Oh.
Yeah. So go ahead.
Is it not common that there's more than one Z bond?
It is not common that there's more than one Z bond. In fact, your body specifically takes trans-retinal after the fact. Once this happens, the protein has been activated, and there's some events that happen downstream that I'll tell you about really briefly that convert that motion into a signal that your brain interprets as vision. But once the molecule is isomerized, your body actually has to go in and clip out that trans molecule, take it somewhere to a place called the retinal pigment epithelial cells, and they isomerize it back to trans with back to cis with enzymes. Then they package it back to the rod and cone cells and they load it in again. So each rhodopsin molecule has to reset after it absorbs a photon of light. And it's crazy that all of this is going on. That's the reason we can all see. It's happening at that rate. Now, this isn't a super deep biochemistry or neuroscience class, and my knowledge of this is really superficial, but it's kind of cool, so I thought we'd talk about it. I know I'll just mention it briefly, and then we'll take a break. It's just kind of cool. And so the question that people always ask when I do something like this is, so should I memorize all of that? And I say, yes, you should memorize all of that. No, of course you shouldn't memorize all of that. I don't have this memorized. If you go into neuroscience or biochemistry, you'll learn more about this. I just want to show you just a flavor of the complexity of the process, because I'm really not satisfied with the explanation, the molecule isomerizes and then that's how you see. I mean, it's true, that's where it starts, but there's an elaborate chain of events. There's no wire going from the receptor cell in your eye to your brain. There's a series of biochemical events that eventually connect to a neural signal, which basically does act as a wire. So with that in mind, this is the rhodopsin protein. This is the 11-cis retinal. You can see it's cis because it's kind of kinked. It looks like a C. Photon of light gets absorbed, and then the rhodopsin changes its shape because the trap is sprung. The retinal becomes trans. It bumps some things out of the way. One thing you need to know about proteins is their shape really matters for their function, just in the same way that the shape of a Phillips head screwdriver is different from the shape of a flathead screwdriver. If you have one, it can do one thing. If you have the other, it can do another thing. The isomerization, the trapdoor action, changes the shape of the rhodopsin protein. It allows it to bind this protein that's called transducin. And when it binds transducin, the alpha subunit of transducin is released, and then it binds another molecule called phosphodiesterase. And this molecule's job is to break apart a signaling molecule inside your cell, which is called cyclic GMP. If you want to see the structure of cyclic GMP, it's actually in your alternative problem set 1. I can't remember assign formal charges. In any case, the esterase hydrolyzes this molecule. Okay? Now are you confused yet? Because we're several events downstream. We sprung the trap with light. The rhodopsin molecule activated transducin, and transducin dissociated its alpha subunit and then activated the diesterase, the phosphodiesterase. And the job of the phosphodiesterase is to chew apart this molecule, cyclic GMP. This is a signaling molecule, a molecule that tells other things in the cell to happen. The beauty is that one rhodopsin molecule can activate multiple transducin molecules. So this is an amplified signal. You can detect one photon in this rhodopsin, and then boom, it sends out many, many, many transducin molecules, which activate many phosphodiesterases. That in turn decreases the amount of cyclic GMP in the cell. When there's a lot of cyclic GMP, there's an ion channel that's open that lets sodium and calcium ions into the cell. When there's not a lot of cyclic GMP, those ions are closed. And so the activity of the diesterase to lower the amount of cyclic GMP closes these ion channels, and that results in a signal that changes the potential of the cell, the electrical potential of the cell, and that's something that downstream nerves can sense. We've just talked about the beginning few steps in this process. This process has been worked out by biochemists. It took a ton of time. It's very intricate, and it's all happening faster than we can explain it in your eyes, and this is how you see. Now, if you look at a bright light long enough, there's an after image, and you can't see very clearly until that after image clears. What's going on is you can overwhelm the signal to the point that the cell is not ready to receive more photons yet. And so that can happen when, anyway, when you see after images, that's part of what's going on. Okay, if you want to know more about this, there's a whole article about it on Wikipedia. That's where I look sometimes for a lot of information. So that's pleasing the eye, gladdening the heart. 11 cis retinal is really, really important. And now you know and can tell your grandma, Grandma, do you want to know what happens when I turn on the light? It gets light in the room? No, the photons excite my 11 cis retinal from HOMO to LUMO. That causes the bond to break, and then you get photoisomerization, which then gets translated into an image. Come on, Grandma, HOMO and LUMO, right? Now you know. All right, let's take a break. I got to go get something up in my office. We'll be back in about 5 minutes.